In the vast, indifferent theater of the cosmos, there are stars that burn, stars that fade, and stars that destroy. But among the hundreds of billions of stellar bodies that populate the Milky Way, one type of object holds a special, terrifying distinction. It is not the largest, it is not the brightest, it is not even the most massive, but it is, by many measures, the most dangerous star in our galaxy. This is a story about a cosmic killer that spins at a rate that defies comprehension, a corpse of a star that packs the mass of a sun into the space of a city, and a gravitational monster that, under the right circumstances, could snuff out our entire solar system in a heartbeat. This is the story of Pulsar J09520607, the heavyweight champion of neutron stars and the galaxy's ticking time bomb. To understand why this particular object is so dangerous, you first need to understand the extreme physics of neutron stars. Imagine the most violent event you can conceive: a supernova, the explosive death of a star at least 8 times the mass of our Sun. When such a star exhausts its nuclear fuel, the core, no longer supported by the outward pressure of fusion, collapses inward at a staggering fraction of the speed of light. Within a second, the core, which was once roughly the size of Earth, is crushed into a sphere just over 6 miles across. This is not a gradual process. The implosion is so violent that the protons and electrons in the core are literally squeezed together, merging to form a sea of neutrons. The resulting object is a neutron star, a ball of the densest observable matter in the universe. Let me give you a specific number to put that density into perspective. A single teaspoon of neutron star material, about 5 milliliters, would weigh roughly 1 billion tons on Earth. That is not a vague comparison to mountains or skylines. That is the mass of a mountain, a literal pile of rock that rises miles into the sky, compressed into a spoonful. But density is only the beginning. The gravitational field at the surface of a neutron star is so intense that if you were foolish enough to drop a small object, say a single penny, from a height of just 1 meter, it would hit the surface with the force of a nuclear explosion. The impact would release energy equivalent to detonating roughly 1,000 hydrogen bombs. And this is just the baseline for a normal neutron star, one weighing about 1.4 times the mass of our Sun. Now, consider Pulsar J09520607. This is not a normal neutron star. Located roughly 5,000 light-years from Earth in the constellation Sextans, this object is a record-breaker. It has a mass of approximately 2.35 solar masses. That is nearly 2.4 times the mass of our entire Sun, squeezed into a sphere that could comfortably sit within the boundaries of New York City. To achieve this mass, the core of the original star had to be enormous. But the real story of how it got so heavy lies in its hungry parasitic behavior. Pulsar J09520607 spins at a rate of 707 revolutions per second. Let me put that number in context. The blades of a typical kitchen blender spin at around 200 to 300 revolutions per second. A helicopter rotor, for comparison, spins at a sedate 5 to 7 revolutions per second. This pulsar is spinning more than 100 times faster than a helicopter rotor. At its equator, the surface is moving at a significant fraction of the speed of light. But why does it spin so fast? The answer involves a cosmic principle known as the conservation of angular momentum, and it plays out in one of the most violent relationships in the galaxy. Pulsar J09520607 is not alone. It has a companion, a white dwarf. A white dwarf is the leftover core of a star like our Sun, a dense, dim cinder that has exhausted its nuclear fuel. But in this system, the white dwarf is in a death spiral. The neutron star's immense gravity is literally tearing it apart. Material from the white dwarf, superheated plasma, streams across space and crashes onto the surface of the pulsar. This process, called accretion, transfers mass and, crucially, angular momentum from the companion to the neutron star. As the white dwarf is devoured, the pulsar spins faster and faster, like a figure skater pulling in their arms, except the skater is a stellar corpse with the destructive power of a supernova. This brings us to a critical point that often confuses people. How can a neutron star, which is made almost entirely of neutrons, have a solid iron crust? It seems paradoxical. The answer lies in the extreme pressure and temperature gradients at the surface. The neutrons in the star are not a uniform soup. At the surface, where the pressure is lower, a thin layer of normal matter can exist. This layer is composed of iron, the most stable element, forged in the supernova explosion that created the neutron star. As you descend deeper, the pressure increases and the iron atoms are crushed. The electrons are squeezed into the atomic nuclei, where they combine with protons to form more neutrons. At a depth of about half a mile, the iron lattice gives way to a dense fluid of neutrons with a sprinkling of protons and electrons. So, the crust is a solid crystalline shell of iron nuclei, roughly half a mile thick, floating on a sea of pure neutron fluid. It is a terrifying structure, rigid and brittle, subject to violent starquakes that can release more energy in a fraction of a second than our Sun produces in a year. Now, let us talk about the centrifugal force argument, because it is central to understanding why Pulsar J09520607 is so dangerously close to its own destruction. A normal, non-spinning neutron star will collapse into a black hole if its mass exceeds a theoretical limit, typically thought to be around 2.1 to 2.3 solar masses. This is the Tolman-Oppenheimer-Volkoff limit, the point at which the neutron degeneracy pressure, the quantum mechanical force that keeps neutrons from crushing each other, can no longer hold up against gravity. But Pulsar J0952-0607 is not normal. It is spinning at 707 revolutions per second. That rapid rotation generates a powerful outward centrifugal force. Think of it like a rock whirled around on a string. The faster you spin, the harder the rock pulls outward. For the neutron star, this outward pull acts against gravity, effectively propping the star up. It allows the star to hold together at a mass that would otherwise be fatal. Scientists calculate that this centrifugal support allows Pulsar J0952-0607 to pack on an extra 10 to 20% of mass beyond the static limit. Without that spin, it would have already crossed the threshold and collapsed into a black hole. But this is not a stable situation. The spinning is not permanent. The pulsar is losing rotational energy through its intense magnetic fields and the beam of radiation it emits. As it slows down, the centrifugal support weakens. The star is essentially coasting on borrowed time. And there is another problem. It is still eating its companion. Every bit of mass it accretes from the white dwarf pushes it closer to the critical point. The pulsar is trapped in a vicious cycle. It spins faster because it eats, but eating makes it heavier, and slowing down will eventually remove the support that keeps it alive. When it finally collapses, it will form a black hole. But the collapse itself will be a cataclysmic event, a gravitational implosion that releases a burst of energy that could be detected across the galaxy. This type of pulsar is known as a black widow pulsar, named after the spider that consumes its mate. The companion white dwarf orbiting PSR B1257+12 is being systematically obliterated. It orbits the pulsar at a speed of over 200 miles per second, completing a full orbit in just over 6 hours. The two objects are so close that the white dwarf is being evaporated by the pulsar's intense radiation and particle wind. Eventually, the white dwarf will be completely consumed, leaving the pulsar alone and dangerously close to the mass limit. At that point, the pulsar's fate is sealed. It will either collapse into a black hole immediately, or it will spin down slowly over millions of years and collapse later. Either way, the result is the same. So, what would happen if PSR J09520607 wandered into our solar system? Let us paint the most terrifying picture possible. Imagine this object, this spinning city-sized sphere of neutron soup, appearing in the orbit of Mars. The effects would be immediate and catastrophic. The pulsar's gravity would tear the solar system apart. Earth, Mars, and the gas giants would be yanked from their stable orbits. The planets would begin to drift, pulled into a chaotic dance around the tiny, super-dense invader. The Earth's atmosphere would be the first casualty. The intense radiation from the pulsar's beam, a lighthouse sweep of gamma rays and X-rays, would strip away our protective blanket. The oceans would boil. The surface would be sterilized within seconds, but the physical destruction would follow. As Earth's orbit destabilizes, it would be drawn closer and closer to the pulsar. Tidal forces, the same forces that cause our oceans to rise and fall, would become so extreme that the planet itself would be torn apart. This is the Roche limit. At a certain distance, the gravitational pull of the pulsar would overcome the internal gravity of the Earth, ripping it into a stream of debris. The rock that was once our home would form a short-lived glowing accretion disk around the neutron star, a final molten funeral pyre. But the destruction would not stop there. The pulsar's gravitational influence would pull in the sun itself. But our sun would not simply be swallowed whole. The sun is a ball of gas, and as it approaches the neutron star, its outer layers would be siphoned off, forming a giant stream of plasma that spirals into the pulsar. This would be a process that could take thousands of years, but it would be a slow, agonizing death for our star. Eventually, the pulsar, having consumed the white dwarf that was its companion, and then the sun, would have accumulated even more mass. With the centrifugal support from its spin fading, it would cross the final critical threshold. The neutron star would collapse. In a fraction of a second, the city-sized sphere would vanish, replaced by a point of infinite density, a black hole. Our solar system would be gone, replaced by a single, silent gravitational pit. This scenario is purely hypothetical, of course. PSR J09520607 is safely thousands of light years away, locked in its deadly dance with its dying white dwarf. But it is not the only dangerous star out there. Far from it. The galaxy is filled with stellar monsters, each with its own unique way of causing destruction. And some of them are far, far stranger. Consider the Magnetars. These are a rare and extreme subclass of neutron star, objects with magnetic fields so powerful that they beggar belief. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's. That is already an incomprehensible number. A magnetar's magnetic field is another 1,000 times stronger than that. To give you a specific comparison, Earth's magnetic field is about half a Gauss. A fridge magnet is about 100 Gauss. A magnetar's magnetic field can be over 1 quadrillion Gauss d. This is a field so intense that it can warp the very shape of atoms. At a distance of a few thousand miles from a magnetar, the magnetic field would be so strong that it would disrupt the electron clouds in your body. Your atoms would be stretched into long, thin cylinders, aligned with the field lines. Your body would be literally torn apart at a quantum level. There would be no pain. There would be no awareness. You would simply cease to exist as a coherent entity, your matter dissolving into a plasma of distorted atoms. Magnetars are also prone to violent starquakes. The extreme magnetic field places enormous stress on the solid iron crust. Periodically, this stress becomes too much, and the crust cracks. The resulting quake releases a burst of energy that is staggering. In a fraction of a second, the magnetar can release as much energy as our sun produces in 100,000 years. This energy is released primarily in the form of gamma rays and X-rays, a blast of radiation that can travel across the galaxy. If a magnetar were located within 10 light-years of Earth, a single starquake would be enough to strip away our ozone layer, leaving the surface exposed to the full fury of the sun's ultraviolet radiation and cosmic rays. The result would be a mass extinction event on a scale that makes the dinosaurs' demise look like a minor inconvenience. Fortunately, the closest known magnetar, designated SGR 1806-20, is located about 8,000 light-years away. But distance is not always a guarantee of safety. In 2004, a magnetar named SGR 1806-20 unleashed a giant flare that was detected by satellites in our solar system. The burst was so powerful that it temporarily disrupted Earth's upper atmosphere, despite originating from the other side of the galaxy. The blast had the energy of 1 billion trillion nuclear weapons. If that same magnetar had been just 40,000 light-years closer, within a few thousand light-years of Earth, the effects would have been catastrophic. The gamma-ray burst would have damaged our satellite networks, caused widespread power grid failures, and exposed anyone on the surface to dangerous levels of radiation. Then there are the pulsars that are not just fast, but bright. The Vela pulsar, located just 1,000 light-years from Earth, is one of the brightest in the gamma-ray sky. It is a spinning neutron star that pulses 11 times per second, a relatively pedestrian spin rate compared to PSR J09520607. But what makes Vela special is the power of its radiation. Its gamma-ray emissions are about 200 times more energetic than those of a standard pulsar. The beam of gamma rays from Vela extends nearly 1 light-year into space. For comparison, that is 15 million times the distance between the Earth and the Moon. If a planet happened to drift into that beam, it would be instantly sterilized. The radiation would rip apart molecules, disrupt DNA, and turn the surface into a scorched, lifeless rock. The Vela pulsar is so close to us that scientists have been able to convert its radio pulses into an audio signal. It sounds like the roaring of a car engine or the beating of a massive mechanical heart. It is a constant, rhythmic reminder of the violence that hums quietly in our celestial backyard. Beyond neutron stars and magnetars, the galaxy is home to stars that are dangerous for entirely different reasons. Take Eta Carinae, a binary system located about 7,500 light-years away. This system contains a pair of hypergiant stars, one of which is incredibly unstable. In the mid-19th century, it underwent a massive eruption, ejecting several times the mass of our Sun into space. The resulting nebula, the homunculus, is a beautiful hourglass-shaped cloud of gas and dust. But if that star ever goes supernova, which it may do at any moment over the next few 100,000 years, the explosion will be one of the most powerful events in our galaxy. It could briefly outshine the combined light of all the other stars in the Milky Way. If Eta Carinae's rotational axis happened to be pointed toward Earth, the resulting gamma-ray burst could be devastating. Such a burst could damage our atmosphere, deplete the ozone layer, and trigger a mass extinction. The danger from Eta Carinae is not imminent, but it is a stark reminder that the galaxy is not a static, peaceful place. It is a dynamic, violent arena where stars live fast and die young. And then there are the stars that are not just dangerous because of what they do, but because of what they are. The galaxy contains stars that are so massive that they are on the verge of collapse into black holes. These are the Wolf-Rayet stars, hot, massive stars that are shedding their outer layers at a furious rate. They are near the end of their lives, burning through their remaining nuclear fuel with incredible intensity. A Wolf-Rayet star, like WR102, which is one of the hottest stars known, has a surface temperature of over 200,000 degrees Celsius. Its surface temperature is over 35 times hotter than the surface of the Sun. The radiation from such a star is so intense that it literally pushes matter away from itself, creating powerful stellar winds. Any planet in the vicinity would be vaporized, its atmosphere stripped, its surface melted to slag. These stars are ticking time bombs, waiting to explode as hypernovae, events that are even more powerful than standard supernovae, and that can leave behind a stellar mass black hole. But perhaps the most dangerous object in our galaxy, at least from a perspective of sheer concentrated malevolence, is the one we have already discussed. Pulsar J0952-0607 represents a unique confluence of factors. It is rapidly spinning, a quality that allows it to pack on extra mass. It is actively accreting matter from a companion, a process that will inevitably push it over the edge. And it is already so close to the critical mass limit that its existence is a precarious balancing act between centrifugal force and gravitational collapse. It is a star that is teetering on the brink of its own oblivion, dragging a doomed companion down with it. Let us delve deeper into the centrifugal force argument, because it is a subtle and beautiful piece of physics. When we say that rapid rotation allows the neutron star to support more mass, we are not just talking about a small correction. The effect is significant enough to allow the star to evade the Tolman-Oppenheimer-Volkoff limit by up to 20%. To understand how this works, consider the forces at play. Gravity is pulling every bit of the star inward, compressing it toward the center. The neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same space, pushes outward. In a non-rotating star, these two forces balance, but when the star rotates, a third force enters the picture. The centripetal force, which is the inward force required to keep matter moving in a circle, acts in the opposite direction of gravity, effectively reducing the net inward pull. At the equator, the effect is strongest. The star bulges outward. This bulging redistributes the mass, allowing a denser core to be hidden beneath a more extended surface. The math is complex, but the result is that a rapidly spinning neutron star can hold together at a mass that would otherwise be fatal. The spin provides a gravitational subsidy, but here is the catch. The spin is not free. The pulsar is emitting energy in the form of electromagnetic radiation and particle winds. This loss of energy causes the pulsar to slow down over time. Every time it loses a little bit of spin, it loses a little bit of that gravitational support. The mass, however, remains the same. So, as the pulsar slows down, it must contract slightly, becoming denser until it reaches a new equilibrium. But this can continue only so far. Eventually, the rotation becomes too slow to provide any meaningful support, and the star, now too massive to be held up by neutron degeneracy pressure alone, collapses. Pulsar J09520607 is not just any pulsar. It is one of the fastest spinning ever discovered. Its spin rate of 707 revolutions per second places it in a very elite club. To achieve that rate, it must have been accreting material from its companion for an exceptionally long time, or it must have been born with an unusually fast spin. Either way, it is a record breaker. And it is not just the spin that is extreme. Its mass is the highest ever confirmed for a neutron star. This combination of fast spin and high mass makes it a unique laboratory for studying the limits of nuclear physics. Scientists are still debating exactly how massive a neutron star can become before it collapses. PSR J09520607 is pushing those boundaries. Now, you might be wondering about the iron crust. How can a ball of neutrons have a solid surface at all? The answer takes us to the edge of our understanding of matter under extreme pressure. The crust is not made of neutrons. It is made of atomic nuclei, primarily iron, packed together in a crystal lattice. This lattice forms because at the surface of the star, the pressure is low enough that normal atomic structure can survive. But as you go deeper, the pressure and density increase. The atoms are squeezed closer together. The electron orbitals overlap, and the electrons are forced into the atomic nuclei, where they combine with protons to form neutrons. At a certain depth, typically around half a kilometer below the surface, the nuclei are so neutron-rich that they become unstable. The lattice dissolves, and the matter becomes a fluid of neutrons, with a small admixture of protons and electrons. This is the neutron star proper. The crust is fascinating because it is brittle. It can crack. When it does, it can trigger star quakes. These quakes are not like earthquakes. They release energies that dwarf any geological event on Earth. The energy released in a Magnetar starquake is comparable to the entire energy output of the Sun over 1 million years. These quakes can cause the pulsar to suddenly change its spin rate, a phenomenon known as a glitch. Astronomers have observed glitches in many pulsars, and they are a valuable tool for probing the interior structure of these objects. All of this brings us back to the central question. Is PSR J09520607 the most dangerous star in our galaxy? It is a strong candidate, Its proximity to the mass limit, its rapid spin, and its predatory relationship with its companion make it a uniquely volatile system. But danger is a relative term. A magnetar is more immediately dangerous due to its magnetic fields, but they are rare. A Wolf-Rayet star will explode in a hypernova, but that event is far in the future. PSR J09520607 is dangerous because it represents a process that is ongoing. It is consuming a star. It is growing. It is approaching a critical phase. It is a star that is actively, right now, changing its own destiny. Perhaps the true danger of PSR J09520607 is not that it will destroy us. It is far too distant for that. The true danger is what it represents. It is a reminder that the universe is not a benign place. Stars are not just sources of light and heat. They are engines of destruction. They are the birthplaces of black holes. They are the factories that forge the elements. And every so often they create an object like this one, an object that dances on the razor's edge between stability and annihilation. It is a cosmic wonder and a cosmic warning. As we look through our telescopes, we are seeing a snapshot of a universe that is violent, chaotic, and indifferent to our existence. The night sky is not a peaceful canopy, it is a battlefield. And in that battlefield, PSR J09520607 is one of the most formidable weapons. It is a star that is literally spinning itself toward destruction, dragging a companion to its doom, and challenging our understanding of physics. It is the most dangerous star in our galaxy, not because it will kill us, but because it embodies the raw, untamed power of a universe that operates on scales and forces that we are only beginning to grasp. And the story does not end there. Our galaxy holds other secrets. There are stars that may harbor black holes in their cores, artifacts from the dawn of time. There are stars that are so faint and dense that they are nearly invisible, drifting through space like cosmic assassins. There are the remnants of stellar explosions that are still expanding, carving out bubbles of emptiness in the interstellar medium. Each of these objects tells a story of creation and destruction, of birth and death. Pulsar J09520607 is just one chapter, but it is a spectacular one. It is a star that, for a brief moment in cosmic time, is one of the fastest, most massive, and most dangerous objects in the galaxy. It will not last forever. Eventually, it will collapse, and a new black hole will be added to the galactic census. But until then, it spins, it pulses, and it consumes. It is a beacon of extreme physics, a lighthouse of danger, and a testament to the infinite creativity of a universe that can conjure such wonders from the ruins of dead stars. The most dangerous star in our galaxy may be thousands of light years away, but its shadow looms large, a reminder that we live in a cosmos where danger and beauty are often one and the same. Yet, for all the danger embodied by PSR J09520607, it is far from alone in the galaxy's rogues gallery. The Milky Way is littered with stellar corpses and unstable giants, each capable of unleashing destruction on scales that dwarf anything humanity has ever witnessed. Consider the neutron star binary system, PSR J07373039, located about 2,400 light-years away. It consists of two pulsars locked in a tight orbit that completes a full revolution every 2.4 hours. Both stars are dead. But their dance is not a peaceful one. They are slowly spiraling inward, losing energy through gravitational waves. In about 85 million years, they will collide. When they do, the merger will release a burst of energy equivalent to the combined output of 1 trillion suns. That kilonova would eject a cloud of heavy elements, including gold and platinum, across thousands of light years. But any planet within a few hundred light years would be sterilized by the gamma-ray flash and the subsequent blast of particles. The two pulsars are a ticking clock, and their collision will be one of the most violent events in our galaxy's future. Then there are the Black Widow and Redback pulsars, neutron stars that are actively destroying their stellar partners, just like PSR B1257+12. But some of these systems are even closer to Earth. PSR B1257+1238, located about 4,500 light-years away, is a redback pulsar that has been observed switching between a state where it is slowly consuming its companion and a state where matter flows onto it in a furious torrent. This pulsar spins at 592 revolutions per second, and its companion is a low-mass star that is being relentlessly stripped. The system is so close that astronomers have watched its behavior change in real time, catching the moment when the accretion disk forms and then vanishes. If the pulsar ever pushes its mass over the limit, it will collapse into a black hole, and the entire system, including the half-eaten companion, will be swallowed. But the danger is not limited to neutron stars. There are massive stars that are so luminous they are literally blowing themselves apart. Take the star NGC3603A1, a binary system in the Carina Nebula. Each star is about 120 times the mass of our Sun. These are among the most massive stars known, and they are so close to each other that their surfaces almost touch. Their orbital period is barely 3.8 days. The radiation pressure between them is so intense that they are shedding mass at an enormous rate. When one of them goes supernova, it will not just explode, it will trigger a chain reaction in its companion, causing a second supernova within months. This double detonation will create a black hole and likely eject the remaining star at tremendous speed, turning it into a hypervelocity runaway. If that runaway star ever passed through the Oort cloud, it would send a hail of comets toward the inner solar system. The chances are low, but the potential for devastation is real. Even more unsettling are the stars that are simply too close for comfort. The red supergiant Betelgeuse, barely 650 light-years away, is in the final stages of its life. It has already shrunk and brightened erratically, leading to speculation that it may explode within the next 100,000 years, perhaps even tomorrow. When Betelgeuse goes supernova, it will be visible during the day, outshining the full moon. But the real danger lies in the radiation. If Betelgeuse's rotational axis points toward Earth, the gamma-ray burst could strip away our ozone layer, exposing the surface to deadly ultraviolet radiation from the Sun. The event would be a natural catastrophe of global proportions. Yet Betelgeuse is not the most dangerous star in the galaxy. It is simply the nearest large star that might explode soon. The true monsters are farther away, but their effects can reach across vast distances. One such monster is the Microquasar SS433, a stellar system that defies easy classification. SS433 is a binary system about 18,000 light-years away. consisting of a black hole or a neutron star, astronomers aren't entirely sure which, and a massive companion star. What makes it so dangerous is the way it accelerates matter. The compact object is pulling gas off its companion, but instead of forming a simple accretion disk, the system launches two narrow, oppositely directed jets of plasma at speeds approaching a quarter of the speed of light. Those jets are precessing like a wobbling top, completing a full rotation every 162 days. As they sweep through space, they carve out a region of violently disturbed gas and high-energy radiation. If Earth were ever caught in the beam of one of those jets, the blast of X-rays and gamma rays would be lethal, even from thousands of light years away. But SS433 is not the only microquasar. A handful of others are known, and some are closer. Their ability to focus destructive energy into narrow beams makes them stealthy killers, a threat that can appear suddenly and devastate a planet without warning. Yet, for all these perils, the most dangerous star remains the one that embodies the very limit of stellar existence. PSR B1257+12 is not the largest, not the brightest, not the most magnetic. It is, however, the star that sits at the knife edge between matter and oblivion. It is a cosmic tightrope walker, and it will eventually fall. When it does, it will create a black hole, a region of space where the laws of physics as we know them break down. That black hole will be the final legacy of a star that once spun faster than any other, that consumed its companion, and that defied collapse for a few precious million years. In the grand clockwork of the galaxy, this is just one more tick. But for those of us watching from our tiny blue planet, it is a reminder of the elegance and the ferocity of the universe we inhabit. The most dangerous star in our galaxy may not threaten us directly, but its existence teaches us that danger is woven into the fabric of space itself. And that is a lesson worth remembering every time we look up at the night sky. Out in the depths of the Milky Way, there is a star that refuses to behave like any other. It doesn't shine the brightest, it doesn't burn the hottest, and it doesn't sit quietly in some familiar corner of the night sky. Instead, it spins at speeds that would tear any ordinary object apart. It is so dense that a single teaspoon of its material would outweigh every mountain on Earth. But that is not even the worst part. The real problem is that this thing is unstable. It is balanced on a knife's edge. One wrong move, just a little more mass, just a little more pressure, and it will collapse into something even worse, a black hole. And the thing is, this is not some distant object on the edge of the observable universe. It is inside our galaxy right now, spinning, feeding, growing. Scientists have known about it for a while. They even gave it a name. But for all the data we have gathered, there is still one question they cannot answer. When is it going to blow? Or maybe the better question is, are we sure it hasn't already? When a massive star reaches the end of its life, it does not go quietly. It burns everything it has, trying to fight off the inevitable pull of gravity. And once its nuclear fuel runs out, gravity wins. The core collapses, the outer layers explode in a supernova, and what is left behind is something strange, something small, something impossibly heavy. What you get is a neutron star. It is not just dead, it is transformed. Now, a typical neutron star is not much bigger than a city, maybe 20 kilometers across. You could drive across it in under half an hour if you could somehow land on it without being crushed or vaporized. But in that tiny space, it holds more mass than our entire sun. That is like taking every person, planet, mountain, and ocean in our solar system and stuffing it into a sphere the size of Manhattan. Because it is so compact, a neutron star has insane density. 1 teaspoon of this stuff would weigh over 1 billion tons. That is more than the weight of every building in New York City combined. If you dropped a piece the size of a sugar cube onto Earth, it would not just sit there. It would punch straight through the crust, tear through the mantle, and keep going until it hit the core. It would not even slow down. But that is just the beginning. Some neutron stars spin, not slowly rotating like Earth, but ridiculously fast. They spin so fast that they flash beams of radiation across space, like the rotating light on a lighthouse. That is what we call a pulsar. Not because it pulses like a heartbeat, but because those beams sweep past us at regular intervals, and they look like pulses when we detect them. At first, scientists had no idea what they were. Back in 1967, when Jocelyn Bell first picked up the rhythmic signals of the first known pulsar, the team did not rule out aliens. That is how strange it was. Something in deep space was sending radio pulses with the timing of an atomic clock. Later, we figured it out. It was not E.T. It was something much weirder. These things spin at hundreds of revolutions per second. That is faster than the blades of a helicopter, faster than your kitchen blender, and in some cases, even faster than a jet turbine. They are cosmic flywheels that dwarf human-made machinery in both speed and endurance. And they do not slow down easily. Many of them have been spinning like this for millions of years. Now, why does a neutron star spin so fast in the first place? It comes down to a simple law of physics: conservation of angular momentum. Imagine an ice skater spinning on the ice. When they pull their arms in, they spin faster. The same principle applies to a collapsing star. When a massive star runs out of fuel, its core collapses from something the size of 1 million kilometers down to something just 20 kilometers across. That dramatic shrinkage forces the core to spin up to incredible speeds, exactly like the skater pulling in their arms. The original star was rotating slowly, but after the collapse, all that rotational energy is squeezed into a much smaller volume. The result is a neutron star that can spin hundreds of times per second. This is not a mechanism that prevents black hole formation. It is simply a consequence of the collapse itself. The spin does not save the star from gravity. It just makes it more extreme. And here is where things get dangerous. Some pulsars do not just exist alone in the void. They find companions, not by choice, but by force, through a process called accretion. Nearby stars are caught in their gravitational grip. Over time, the pulsar gathers enough material from these unfortunate companions. The doomed companion, often a low-mass star, is stripped of its outer layers. Its matter is torn away in a searing stream of superheated plasma. This spiraling torrent of gas funnels into the pulsar, delivering a surge of energy. It spins faster, it gains mass, it becomes more extreme. Scientists call these black widow pulsars. Just like the spider, they consume their mate after mating. Only in this case, the pulsar does not just kill its companion, it eats it atom by atom. This process does not go on forever. There is a limit to how much mass a neutron star can hold. And once it gets too close to that line, the structure cannot hold anymore. The neutron pressure fails. Gravity takes over, and the pulsar collapses again. This time, into a black hole. So, when we say some of these stars are dangerous, it is not because they are going to explode and send shock waves across the galaxy like a supernova. It is because they are already past the point of being ordinary stars. They are dense, powerful, spinning time bombs. And the one we are focusing on is not just any pulsar. It is the fastest spinning, heaviest neutron star ever discovered. And it is sitting right here in our own galactic neighborhood. Let me show you what makes this one different. Not all pulsars are equal. Most of them spin fast, yes. Most of them are dense and powerful. But every once in a while, astronomers find something that does not just fit the definition, it redefines it. One of those is called PSR B1257+12. It does not have a flashy nickname, and it is not in a sci-fi movie. But what it does have is a resume that reads like a warning label from the universe itself. This thing spins at 707 revolutions per second. That is not a typo. Every second, it completes over 700 full rotations. You could not even blink that fast if you tried. It is so fast that its surface is moving at a significant fraction of the speed of light. And yet, it is not flying apart. Gravity holds it together, squeezing it so tightly that even atoms themselves do not exist on the surface anymore. The only thing left is neutron matter, crushed so hard that electrons and protons have merged. And as if that were not enough, it is also the heaviest neutron star ever discovered, nearly 2.4 times the mass of the Sun, all crammed into a space just 20 kilometers wide. That combination, extreme spin and near critical mass, is why this object is dangerous. Because here is the catch. Neutron stars are not supposed to weigh that much. The upper limit, the so-called Tolman-Oppenheimer-Volkoff limit, is estimated to be somewhere around 2.5 to 3 solar masses. Beyond that, the neutron pressure can no longer resist gravity, and the star collapses into a black hole. So, this one is close, really close. And we now know how it got this way. It was not born this massive. It ate its way here. Orbiting this pulsar is the dim, fading remnant of a star, a white dwarf that is being slowly ripped apart. Like a drop of water falling into a drain, its matter spirals toward the pulsar. Some of it falls in. Some of it forms a hot, glowing accretion disk. Either way, the pulsar gains mass. It also gains spin, just like an ice skater pulling in their arms, shrinking. The radius increases the angular momentum, and the more it feeds, the faster it spins. That is what makes these kinds of systems so extreme. The process does not just accelerate the pulsar, it puts it under pressure. Every gram of stolen matter is one step closer to the breaking point, one step closer to collapsing. Astronomers call it a black widow pulsar, and the analogy fits. The pulsar drains its partner until nothing remains. The white dwarf fades, the pulsar grows, and eventually there is nothing left but one unstill overfed neutron star waiting for a final push. Now, let us be very clear about something here. A white dwarf being cannibalized by a neutron star does not become a black hole on its own. In other contexts, white dwarfs in binary systems can accrete material, and if they cross the Chandrasekhar limit of about 1.4 solar masses, they can detonate in a spectacular Type Ia supernova. That is a different beast entirely. In this case, it is the neutron star itself that is gaining mass, inching ever closer to its own collapse into a black hole. The white dwarf is just the fuel source, the unfortunate victim being drained to feed the monster. So the danger here is not a supernova from the white dwarf. The danger is the neutron star becoming too heavy to exist. And here is where the reality of the situation sinks in. Unlike a supernova, which announces itself with a visible explosion, this collapse would not give us much warning. There would be no flash of light, no giant shockwave, just a sudden silence. The pulses stop, and in that silence, a black hole is born. We do not know when that will happen. Could be 1,000,000 years from now, could be tomorrow, could already have happened, and we are just waiting for the news to travel about 14,000 light years to reach us. And just so we are clear, this object is inside our own galaxy. It is not some distant curiosity in a faraway cluster. This is a ticking time bomb spinning at full throttle right here in the Milky Way. And the only reason it has not turned into a black hole yet is that it still holds itself together by sheer rotational momentum. The spin is buying it time, but eventually, time runs out. So let us say it happens. Let us say this pulsar finally crosses that invisible line. It pulls in just enough mass from its dying companion, and the delicate balance holding it together breaks. What exactly happens next? Well, the star does not explode, not in the way we are used to thinking about explosions. It collapses silently, instantly. One moment, it is a pulsar, spinning, beaming, pulsing like a galactic lighthouse, and the next, it is gone. The pulses stop. The light vanishes. The radio waves we have been picking up from Earth just cut off. No sound, no flash, just the flick of a switch. And what is left behind is a black hole. This is where the real physics kicks in. Unlike a supernova, which throws off most of the star's mass in a burst of light and gas, a pulsar collapsing into a black hole does not leave behind anything visible. There is no outer shell to eject. The material is already compacted as far as it can go, so the collapse is clean, direct, efficient. The mass is still there, but now it is hidden behind an event horizon. The gravitational pull becomes so strong that even light cannot escape. From the outside, the object becomes invisible, but its presence is still felt. Space around it warps, time slows near it, and anything too close falls in. Here is the good news. Even if this happened tomorrow, we would not feel a thing here on Earth, at least not for a while. This pulsar is about 14,000 light years away, so if it collapsed today, the effects would not reach us for another 14,000 years. Technically, it might have already collapsed. We are still seeing the version of it that existed 14 millennia ago. The light we detect, the pulses we measure, are delayed snapshots from the past. But let us say, for the sake of curiosity, that it did collapse. What does that mean for the surrounding region of space? When a pulsar collapses into a black hole, it loses the structure that was keeping its radiation beams aligned. The regular pulse ends, but its environment does not instantly calm down. The accretion disk, all that material still spiraling in, keeps feeding it. But now, it is not feeding a pulsar. It is feeding a newborn black hole. This can briefly create something called a relativistic jet, an ultra-energetic beam of particles and radiation shooting out from the poles of the black hole, accelerated to near light speed by magnetic fields and rotational energy. If those jets happen to point anywhere near our direction, even from 14,000 light years away, they could do real damage. That is not speculation. It has happened before. Astronomers suspect that a mass extinction event around 440 million years ago, the late Ordovician extinction, might have been caused by a gamma-ray burst from a nearby neutron star or black hole. It would not have hit Earth like a bomb. Instead, it would have silently fried our ozone layer, leaving the surface exposed to ultraviolet radiation from the sun. The result would have been a global collapse of ecosystems, especially marine life. Again, that is rare, unbelievably rare, and the odds of this pulsar's beam being aligned with us are even lower. Most of the time, these jets shoot off in random directions, and the vastness of space is usually enough to keep us out of the line of fire. Still, the point is, it can happen. And that is why scientists keep watching. But let us flip the question now. What if it did not collapse all at once? What if it kept growing slowly, pulling in more mass, increasing pressure, getting closer and closer to that critical point, while still spinning at 707 times per second? At some point, it reaches a stage where even the spin cannot save it. And then, in the blink of an eye, the entire structure gives way. Some models suggest this could unleash an extremely fast, short-lived burst of gravitational waves, ripples in space-time itself. Detectors like LIGO and Virgo might catch it, giving us a real-time signature of a pulsar collapsing into a black hole. That would be a scientific first, but it would also be a cosmic testament, a signal that one of the fastest, densest, most extreme stars in the galaxy just died a second death, quietly, without warning. And what replaces it? An invisible void, a gravity well from which no light can escape. The beam that once pulsed across the galaxy like a clock is gone. From a cosmic perspective, that is the end of the story. But from ours, it is just getting started, because there is another kind of neutron star that does not wait for collapse to be dangerous, one that does not need to spin at 700 times per second to cause havoc. It is not faster. It is not heavier. It is just magnetic. You would think that a star spinning hundreds of times per second, weighing more than our sun, and teetering on the edge of collapse would be the worst-case scenario. But nature, as always, has a way of going further. Because there is another kind of neutron star out there. It does not spin as fast. It does not have to. It does not need a companion star to devour. It does not rely on beams of radiation to make its presence known. Instead, it warps the very structure of matter with something far more silent and far more terrifying. It is called a magnetar. Now, take everything we know about neutron stars, the density, the gravity, the compactness, and add a magnetic field so intense that it can literally tear atoms apart, not just ionize them like regular radiation does, not just heat them up. It rips apart the structure of matter itself. A typical pulsar already has a magnetic field trillions of times stronger than Earth's, but magnetars crank that number up so high that it stops being relatable. The field of a magnetar can be over 1,000 trillion times stronger than Earth's. If you were anywhere near one, even thousands of kilometers away, your atoms would not hold together. The very chemistry of your body would fall apart under the magnetic pressure. And it is not just theoretical. We have observed their effects. In 2004, a magnetar named SGR 180620, located about 42,000 light-years away from Earth in the constellation Sagittarius, released a burst of gamma radiation so intense that it caused sensors on multiple satellites to overload, even though it came from the other side of the galaxy. For a fraction of a second, that Magnetar outshone every other X-ray source in the sky combined. If it had been just 10 light-years closer, Earth would have been in serious trouble. Because unlike pulsars, which spin and fade gradually over time, magnetars are unstable. Their magnetic fields do not stay quiet. They build up tension beneath the crust, and sometimes the pressure becomes too much. This causes what is called a starquake. Imagine a planet-sized object made of ultra-dense neutron matter cracking open like an egg under too much pressure. The crust shifts, the magnetic field suddenly realigns, and the resulting release of energy is so massive that it makes our most powerful nuclear weapons look like firecrackers. These quakes unleash bursts of gamma and X-ray radiation that travel across space at the speed of light. And there is no warning, no build-up, just a sudden flash. The energy of 100,000 suns released in a fraction of a second. We are lucky, by the way. The closest known magnetar is about 8,000 light-years away. That is far enough that even a massive flare would not do much damage to Earth. But scientists have calculated that if one went off within about 40 light-years, it could strip away our ozone layer, exposing the planet to deadly ultraviolet radiation from the sun. And here is the kicker. Magnetars do not live long. Their intense magnetic fields decay quickly over just 10,000 to 100,000 years, which is a blink of an eye in cosmic terms. That makes them rare. For every 1,000 neutron stars, only about 10 are expected to be magnetars. But that is still enough. One is enough. The magnetic field is so powerful that even when the magnetar is quiet, it is still affecting its surroundings. Any nearby planets, assuming they even exist, would be constantly bathed in high-energy radiation. And if a flare did happen while a planet was close, the result would be instant sterilization. You do not need a supernova. You do not need a black hole. You just need a crack in the crust, and it is game over. That is what makes magnetars a different kind of danger. They do not announce themselves with pulses. They do not get louder over time. They are like cosmic mines sitting in place, quiet, waiting. And if the conditions line up just right, they detonate. So, we have got neutron stars that spin fast enough to create artificial-looking beacons. We have got magnetars that hold the record for the strongest magnetic fields in the known universe. And we have got at least one pulsar in our own galaxy that is balancing on the edge of collapse. But let us ask the next logical question. What if one of them was closer? What if somehow one of these stars drifted into our neighborhood? So far, everything we have talked about has felt distant. 14,000 light-years, 42,000 light-years. Even the nearest magnetars are thousands of light-years away, comfortably tucked away behind an ocean of space. And that is probably why most people do not feel the weight of it. Cosmic danger, when far enough away, does not feel real. But let us bring it closer. Let us say one of these neutron stars, does not matter if it is a pulsar, a black widow, or a full-blown magnetar, somehow got kicked in our direction. Maybe from a supernova explosion, maybe a gravitational nudge from another star. Space is chaotic, and neutron stars have been known to move. In fact, some of them are moving at speeds of over 1,500 kilometers per second, fast enough to leave the galaxy entirely. Now, imagine one of those stars, maybe even PSR J09520607 itself, somehow found itself within the orbit of Jupiter. Let us say it parked itself about 500 million miles from Earth. That is still far, right? Jupiter is out there, no big deal. Think again. First, the gravity. Even from that distance, the gravitational pull of a neutron star that massive would start disrupting the orbits of nearby planets. Jupiter, Saturn, and even Uranus might experience orbital shifts. Over time, their paths would destabilize, creating gravitational chaos that trickles inward toward Earth. Then comes the radiation. A pulsar like J09520607 does not just sit quietly. It emits twin beams of high-energy radiation from its magnetic poles, beams made of X-rays, gamma rays, and charged particles. If Earth happened to be in the path of even one of those beams, we would be in serious trouble. Our magnetic field would offer some protection for a while, but the intensity would eventually overwhelm it. The ozone layer would be the first to go. Without it, solar ultraviolet radiation would begin sterilizing the surface, and it would not stop there. The constant exposure to high-energy particles would start breaking molecular bonds in the atmosphere. Satellites would malfunction, GPS would be lost, radio communications would collapse, the night sky would be flooded with unnatural light, and the auroras, those dancing green lights near the poles, would spread across the entire planet, flickering non-stop like a warning. And if it is a magnetar instead of a pulsar, well, the rules change. A magnetar does not need to spin at 700 times per second to cause chaos. All it needs is proximity. If it were within just a few thousand kilometers, the sheer strength of its magnetic field would start pulling at the electrons in the atoms that make up your body. You would not even see it coming. Your body's structure would simply dissolve, not from heat, not from radiation, just raw magnetic force. And even if you were watching from a distance, say from the moon, the view would not be much better. Earth would start to deform, not all at once, but slowly. Tides would go wild, the crust might shift, volcanoes would awaken from dormancy as the pressure underneath builds. Earthquakes would ripple through continents as the gravitational stresses mount. Eventually, the atmosphere itself could be stripped away, blown into space by radiation pressure and magnetic interference. The oceans would boil, then evaporate. The surface would be scorched. Life would vanish, not in centuries or decades, but in hours. And yet, for the neutron star, none of this would be noticeable. To a pulsar or a magnetar, Earth is just another rock, a piece of space debris that happened to get too close. Our sun is barely a snack. If the neutron star had enough mass, or if it kept pulling matter in through an accretion disk, it could eventually collapse into a black hole right there in our solar system. At that point, gravity would dominate completely. Planetary orbits would collapse inward. The sun itself would spiral toward the event horizon and vanish. And that would be the end of the story. Now, obviously, the odds of this happening are extremely low. Neutron stars are fast and powerful, but space is vast. Most of them are traveling through the galaxy in isolation. And even though a few 100 million exist in the Milky Way, the chances of one wandering into our backyard are lower than winning the lottery every day for the next century. But that is not really the point. The point is, these objects exist. They are real, and they are not rare. They are scattered all across the galaxy, some spinning faster than any human-made machine, some glowing with invisible beams of deadly radiation, some with magnetic fields strong enough to destroy planets without ever touching them. And some of them somehow have planets of their own. After everything we have said about neutron stars, the gravity, the radiation, the magnetic fields that could tear atoms apart, it would be fair to assume that nothing could survive near them. Certainly not something as fragile as a planet, and yet a few have. Not many. In fact, only about 0.5% of all known pulsars have been found to host planets. That is out of the thousands we have detected. But those rare exceptions raise a strange question. How can a planetary system survive around one of the most violent objects in the galaxy? Let us start with the basics. Most stars form planets from leftover material, the gas and dust swirling around them during their early life. But pulsars are formed in the exact opposite way, from destruction. A massive supernova explosion wipes everything out, and what is left behind is a crushed core spinning like a blender with a magnetic field that could sterilize entire solar systems. So, the original planets are gone, which means that if a pulsar has planets, they either formed after the supernova or they were somehow captured later. One of the most well-known examples is PSR B1257+12, located about 2,300 light-years away. It was the first pulsar ever found to host planets. And believe it or not, it was also the first confirmed discovery of any exoplanets at all, back in 1992. This pulsar has 3 known planets, all of them rocky, all of them bigger than Earth. And what is strange is that they orbit in relatively stable paths. Not normal circular orbits like we see in our solar system, but highly elliptical, meaning they swing close and then far away as they loop around. The gravitational environment around a pulsar is so intense that even small deviations become amplified. So the fact that these planets are still there and still orbiting is weird. Now imagine living on one. This would not be like Earth. The skies would not have sunlight or a blue atmosphere. They would be black, permanently. Your sky would flash regularly with bursts of radiation, depending on whether the pulsar's beam crossed your location. Instead of sunlight warming the planet, you would get occasional pulses of high-energy particles, enough to sterilize any exposed surface. The only chance for life to exist would be deep underground, shielded by miles of rock, maybe under thick ice, maybe in subsurface oceans. Some scientists think these planets might have formed from supernova debris, material that did not escape into space, but fell back inward and eventually cooled into a dusty disk. Over millions of years, that material could have clumped together into rocky worlds. Others think the planets might be fragments, pieces of a companion star that was shredded by the pulsar's gravity, like cosmic leftovers compressed into orbit. There is also the possibility that these planets were captured, rogue planets drifting through space, caught by the pulsar's intense gravitational pull. This is less likely, but not impossible, especially if the pulsar once had a companion star that got ripped apart and left behind planetary debris. Regardless of how they formed, these planets are survivors. They have withstood radiation, magnetic storms, and gravitational chaos, and they still orbit quietly around one of the most dangerous objects in existence. Another pulsar, PSR B1257+12, has at least 2 known planets. Again, both several times more massive than Earth. One completes an orbit every 1.9 years. The other takes 3.6 years. And just like with B1257+12, their paths are not smooth or gentle. They are elongated, chaotic, and constantly shifting, like a car trying to drive in a hurricane. The weirdest part is that we do not know how rare this really is. We have only detected pulsar planets around a handful of neutron stars, but that might just be because they are hard to see. After all, we are trying to spot tiny worlds orbiting objects that are barely the size of a city across thousands of light years of space, and yet they are out there. If life ever did evolve on one of these worlds, it would have to be unlike anything we can imagine. It would not just have to survive harsh conditions. It would have to be built for radiation, for chaos, for sudden bursts of energy that could melt an atmosphere in minutes. Which brings us back to Earth. We orbit a calm, steady yellow star. We have a mild magnetic field, a breathable atmosphere, liquid water on the surface. In every possible way, our solar system is unusually quiet. The fact that neutron stars can even have planets just makes it clearer how strange and lucky our situation really is. But let us circle back now, because this whole story started with a title, The Most Dangerous Stars in the Universe. And the question is simple: should we be worried? We have talked about stars that spin faster than jet engines, crush matter tighter than atomic nuclei, and shoot beams of radiation that could melt the surface of a planet. We have looked at pulsars that are eating their companions alive, and magnetars that could crack open like lightning-filled eggs and blast radiation across light years. It sounds like a horror movie, but here is the truth. No, we do not need to worry. Not in the way people usually think about danger. PSR B1257+12 is not about to collapse into a black hole tomorrow and erase us from existence. Magnetars are not hovering nearby, ready to fry our atmosphere. These things are real, but they are also far. That is what saves us. Space, as it turns out, is still very, very big. The most dangerous stars in our galaxy might explode, yes, but any minute in cosmic terms could mean tens of thousands of years or longer. And if something like that did happen, the radiation would take just as long to reach us. So even if the collapse already happened, we would not know. We would be staring into the past like we always are when we look at stars. But that does not mean these things are irrelevant. Pulsars, neutron stars, and magnetars are not just freak objects floating in the void. They are reminders that the universe does not run on comfort. It runs on physics, on pressure and collapse, on spin and radiation, on gravity pulling things inward until they cannot hold their shape anymore. These stars show us what happens when things are pushed to their absolute limit and beyond. They tell a story that is less about threat and more about scale. Because what we call normal, a calm star, a stable orbit, an atmosphere that protects us, that is the exception. Most of the universe is rough, unforgiving, full of energy being released in ways we can barely understand, by objects we would never survive being near. So no, we are not in immediate danger, but yes, we should pay attention. Because somewhere not that far from here, a star is spinning itself apart, gaining mass, losing stability, getting closer to the edge. And when it goes, it will not leave a warning. And if you are someone who finds comfort in the stars, remember that not all of them are friendly. Some of them are just waiting to collapse. That is the quiet horror of the cosmos. It is not that these monsters are coming for us. It is that they are out there at all, doing what they do, indifferent to everything we call home. And the only reason we are safe is that we happen to be in the right place at the right time, living on a quiet little planet, orbiting a quiet little star, in a quiet little corner of a galaxy that is, at this very moment, full of stars that are anything but quiet. In the deep black of space, somewhere beyond the dust and darkness of the galactic plane, a star burns so wide that light itself takes most of a working day just to cross from one side to the other. If you dropped our entire solar system next to it, the star would swallow every planet, every asteroid, every comet, and still have room left over. The star we are talking about is a red hypergiant, a celestial monster that pushes against the very laws of physics. But before we meet that beast, we need to understand why such giants exist at all, how they hold themselves together, and why nearly everything we think we know about stellar size comes with a giant question mark attached. This is the story of the biggest star in the universe. Not just one star, but the search for the ultimate champion, the current record holder, the theoretical limits that prevent stars from growing even larger, and the ghosts of giants that may have already exploded before humans ever looked at the sky. Let us begin with a simple fact. When you step outside on a clear afternoon and look up at that blazing yellow disk, you are staring at a star, our star. For most of human history, we assumed it was the center of everything, the biggest, brightest thing in existence. And then we learned how wrong we were. Our sun is about 865,000 miles across. You could line up 109 Earths across its face. You could pack more than 1 million Earths inside it. Those numbers feel impossibly huge until you realize that in the family of stars, the sun is small, almost forgettable. It is an average yellow dwarf, nothing special. Now imagine every grain of sand on every beach on Earth represents a star. Our sun would be one of the smaller grains, lost in a desert of giants. Some grains in that desert are the size of basketballs, some the size of buildings, a few the size of entire cities. Astronomers measure stars using something called solar radii. One solar radius equals the distance from the sun's core to its surface. So when scientists say a star is 1,000 solar radii wide, they mean its diameter is 1,000 times that of our sun. The numbers we are about to explore reach into the thousands, some past 2,000. That means you could drop our sun next to these giants and it would become invisible, a pinhead next a basketball. But here is the first big insight. The size of a star is intimately tied to its color. And color is not about motion, it is about temperature. A red star is cool, around 3,000 degrees Fahrenheit at its surface. A yellow star, like our sun, is warmer, about 10,000 degrees. White stars are hotter still. Blue stars are the elite, burning at 20,000 degrees and beyond. Blue giants are the stars that carve out the most extreme lives, but red supergiants and hypergiants are the ones that swell to ridiculous dimensions. Why does color matter? Because the temperature determines how much energy the star radiates per unit area. A cooler surface means the star must be enormous to produce the blinding amount of light we see from across hundreds or thousands of light years. That is how we spot these monsters. They are stupidly bright, yet they look red. The only way that works is if they are huge. So how do we even measure something that appears as just a point of light in even the most powerful telescopes? Astronomers use a clever trick. First, they figure out the distance using parallax, the apparent shift of a nearby star against distant background stars as Earth moves around the sun. Once the distance is known, they measure the star's apparent brightness and its color. From the color, they get the surface temperature. Then they apply a law of physics called the Stefan-Boltzmann law, which relates how much energy a glowing object emits to its size and temperature. If you know how bright the star truly is and how hot its surface is, you can solve for its radius. It is a beautiful piece of mathematics that turns a single point of light into a cosmic ruler. But there is a catch. The most enormous stars are often shrouded in the material they themselves have ejected, cloaked in dust and gas that can distort the measurements. Some stars change size dramatically as they pulse, and the light from the most distant giants takes thousands or tens of thousands of years to reach us. So when we look at these monsters, we are looking at a snapshot from the past, and some of those snapshots are already lies. The stars that sent them might already be dead. We might be observing ghosts. Let us take a tour of those giants, starting with a star that taught astronomers a hard lesson about brightness and distance. Look up at the winter night sky and find Sirius, the dog star, the brightest star visible from Earth. The ancient Egyptians built calendars around it. Polynesian sailors navigated by it. For centuries, astronomers assumed Sirius must be a giant because it outshone everything else. They were tricked. Sirius is only 8.6 light-years away, making it one of our closest stellar neighbors. Its brightness comes from proximity, not size. In reality, Sirius measures just 1.7 times wider than our Sun. A modest jump, hardly a giant at all. The night sky lies to us. A flashlight held close looks brighter than a stadium spotlight a mile away. Sirius was the master illusionist that fooled astronomers for generations. But Sirius also had a secret. In the 1840s, astronomer Friedrich Bessel noticed it wobbling slightly as it moved through space. Something invisible was tugging on it. He predicted a hidden companion. Years later, telescopes caught a faint glimmer beside the bright star. They named it Sirius B. And Sirius B turned out to be a corpse, the burnt-out core of a once mighty star, now compressed into an object the size of Earth, but holding nearly the mass of our Sun. A teaspoon of its material would weigh several tons. That was the first confirmed white dwarf, and it taught astronomers something profound. To find the true giants of the universe, you cannot trust your eyes. The real monsters often hide farther away, dimmer to our view, but bigger than anything close by could dream of being. So, astronomers started hunting deeper. Their first major prize was in the constellation Orion at the Hunter's Foot, a point of cold blue-white light called Rigel. Rigel sits about 860 light-years away. Its light left that star around the time medieval knights were riding through Europe. And despite that vast distance, it still ranks as one of the brightest stars in our night sky. A star that bright, that far away, has to be a beast. Rigel measures about 78 times wider than our Sun. If you swapped our Sun for Rigel, the inner planets would be incinerated instantly. Mercury, Venus, and Earth would be inside the star. And Rigel pumps out 120,000 times more energy than our Sun every second. That blue color is the giveaway. Blue stars burn at over 20,000 degrees Fahrenheit. They burn through their fuel at a terrifying pace. While our Sun has happily burned for 4.5 billion years and has another 5 billion ahead, Rigel is only about 8 million years old and will explode as a supernova within a few million years, a heartbeat in cosmic time. When it goes, it will outshine every star in the night sky combined. People on Earth, if humans still exist, will see a second Sun appear at night. But as impressive as Rigel is, it is just a teenager among supergiants. The real monsters are the red ones. Turn back to Orion's shoulder. That deep orange-red ember is Betelgeuse. Betelgeuse is a red supergiant about 640 light-years away. It measures somewhere between 700 and 900 times wider than our Sun, depending on when you measure it, because the star pulses. Drop it into our solar system, and it would swallow Mercury, Venus, Earth, Mars, and the entire asteroid belt. Its outer atmosphere would brush against Jupiter's orbit. Our planet would not just burn, it would be inside the star. Betelgeuse is not stable. Its surface boils with convection cells larger than the orbit of Mars. The whole star breathes like a living thing. In late 2019 and early 2020, Betelgeuse dimmed dramatically. People wondered whether the star was about to explode. Astronomers discovered that the star had ejected an enormous cloud of dust that blocked some of its light. The dimming was a warning. Stars this big do not behave nicely as they approach death. They convulse, they throw off material, they flicker. Betelgeuse will explode as a supernova sometime in the next 100,000 years. Possibly tonight, possibly tomorrow, possibly 50,000 years from now. When it does, the show will be unforgettable. It will become brighter than the full moon, visible during the day. At night, it will cast shadows. And because the light takes 640 years to reach us, the explosion may have already happened. The signal might be racing toward us right now. Moving south toward the constellation Scorpius, we find another red supergiant with a name that means rival of Mars. Antares. Antares lies about 550 light-years from Earth. Its diameter stretches about 700 times that of our Sun. If placed where our Sun sits, its outer edge would extend past Mars and reach almost to Jupiter. Earth would be vaporized in a flash. Antares burns at a cooler temperature, around 6,000 degrees Fahrenheit, which is why it looks red. Despite the cooler surface, it puts out nearly 70,000 times the energy of our Sun because of sheer size. Antares is dying, fusing heavier elements in its core. It is currently cooking carbon, oxygen, and neon. Each new fuel buys less time. The carbon stage might last 1,000 years. The neon stage might last a year. The final stages take days. When Antares finally explodes, the supernova will briefly outshine the full moon. But Antares is not the largest red supergiant, not even close. There are stars that make it look like a candle. Deeper in the northern sky, in the constellation Cepheus, sits a star so red that the great astronomer William Herschel nicknamed it the Garnet Star in the 1700s. Its formal name is Mu Cephei. It is about 2,500 light-years away. Its light has been traveling since the time of ancient Greece. Estimates of its size vary, but it is roughly 1,400 times wider than our Sun. Drop it into our solar system, and it would swallow everything out to the orbit of Saturn. Earth, Mars, Jupiter, all gone. Mu Cephei pulses irregularly, its brightness changing over cycles of 2 to 12 years. It also leaks material constantly, forming a faint luminous fog around itself. Mu Cephei emits about 350,000 times the light of our Sun, most of it in infrared. If our eyes could see infrared, it would dominate a large patch of the night sky. Then there is V354 Cephei, a star that breaks what we think of as normal celestial mechanics. V354 Cephei is a red hypergiant about 5,000 light-years away. It measures between 1,000 and 1,600 times wider than our Sun. That range exists because the star is so chaotic. If it replaced our Sun, its outer atmosphere would extend past Saturn. But here is the strange part. VA has a companion star, VB, which is itself massive, about 10 times wider than our Sun and burning blue hot. The smaller star actually skims through the outer layers of the bigger star during part of its orbit. It plows through the giant's puffed-up gaseous envelope every 20 years, stirring up massive amounts of material, creating shock waves and bizarre brightness changes. Nothing about this setup is stable. Eventually, the gravitational chaos will rip the system apart or merge the two stars. These monsters are so loosely held together that their average density is incredibly low. In the outer layers, the gas is thinner than the air inside a vacuum chamber on Earth. Most of the mass is concentrated deep in the core. So how do these stars hold themselves together? They hold together through a delicate balance between gravity pulling inward and radiation pressure pushing outward. In the core, nuclear fusion produces a flood of energy. That energy, in the form of photons, slams into atoms and pushes them away from the center. For most stars, gravity easily wins and the star stays compact. But for these hypergiants, the radiation from the core is so powerful that it almost overcomes gravity. The star skirts the edge of a physical boundary called the Eddington limit. Beyond that limit, the outward push would blow the star's outer layers completely away. These giants survive because they are constantly shedding mass, bleeding material into space in a slow, controlled disintegration. Strong magnetic fields may also help contain the outward pressure, though astronomers are still figuring out the details. One hypergiant that pushed astronomers to the edge of their equations is KY Cygni, in the constellation Cygnus. It sits about 5,000 light-years away. Early measurements put it at nearly 2,050 solar radii, which would have made it one of the biggest stars ever discovered. But that number broke the models. If KY Cygni were that large, it would violate the Eddington limit. So astronomers rechecked the data, accounting for dust that affects brightness readings. Newer estimates brought it down to about 1,030 to 1,400 solar radii. Still a monster, but no longer a paradox. The story of KY Cygni reveals how messy the leaderboard is. Measurements depend on dust, distance, brightness assumptions, and which model of stellar physics you use. A star that looks like a champion one year might be downgraded the next. Another extreme giant hides at the edge of our galaxy, about 9,000 light-years away. It is called V354 Cephei. It measures between 600 and 890 solar radii, depending on the measurement. At its largest, it would extend past Jupiter's orbit. What makes V354 Cephei interesting is its location on the outer fringes of the Milky Way, far from the crowded core where most massive stars are born. How did a monster get so big out there? Possibly it drifted outward over millions of years, or it is the lone survivor of a cluster of massive stars that has since dispersed. Whatever its origin, V354 Cephei is in the late stages of its life, fusing heavier elements and throwing off material that will seed future stars and planets. Now, we travel to a truly bizarre star cluster about 12,000 light-years away in the constellation Ara. It is called Westerland 1, and it is a stellar nursery on steroids. Inside this cluster, dozens of massive stars are crammed into a tiny pocket of space. The undisputed king of Westerland 1 is Westerland 1-26, a red supergiant possibly verging on hypergiant status. Size estimates range from 2,000 to 2,500 solar radii. If correct, that places it firmly among the largest stars ever measured. Drop it into our solar system, and its outer edge would extend past Saturn, possibly toward Uranus. Westerland 1-26 sits dangerously close to the Eddington limit, possibly even crossing it. How does it hold together? Strong magnetic fields may wrap around the giant like invisible webs, and the star is likely losing material fast enough to prevent immediate destruction. Westerlund 1-26 is also surrounded by a huge shell of radio-emitting material, one of the brightest natural radio sources in our part of the galaxy. The entire cluster is only about 4 to 5 million years old, a baby in stellar terms, yet the star has already aged into a red supergiant. It will not last much longer. Within the next few 100,000 years, it will explode. Leaving our galaxy entirely, we travel about 160,000 light-years to the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. Inside it lurks one of the most extreme stars ever discovered, WOH G64. It is a red hypergiant with a diameter estimated at around 1,540 solar radii. But what makes it truly bizarre is what surrounds it. The star is wrapped in a thick, dense torus of dust, a donut-shaped cloud of material that the star itself has been throwing off for hundreds of thousands of years. The torus is so thick that it obscures most of the star's light from our perspective. Looking at WOH G64 is like trying to see a light bulb through a wool blanket. The dust shell stretches for about 120 trillion miles and contains material equivalent to several times the mass of our Sun. WOH G64 is shedding mass at one of the highest rates ever recorded, losing a sun's worth of material every 10,000 years. It is essentially eating itself from the outside in. Closer to home, but even stranger, is the star RW Cephei in the constellation Cepheus. RW Cephei is a yellow hypergiant, though its color shifts unpredictably. It lies about 3,500 light-years away. Its size varies wildly, from 900 to 1,600 solar radii, because the star physically swells and shrinks. RW Cephei is in a transitional phase of its life, caught between being a red supergiant and a stripped-down Wolf-Rayet star. It is not even spherical. Recent observations suggest it has bulges and dimples on its surface, huge convection cells that make it look lumpy like a glowing apple beginning to wrinkle. It throws off material in bursts rather than steadily. In recent years, it dimmed significantly due to a major dust ejection event, similar to what Betelgeuse did. Another hidden giant is NML Cygni, about 5,300 light-years away. It measures between 1,100 and 1,600 solar radii. It is so dim from Earth because it is wrapped in an enormous shell of dust that absorbs almost all of its visible light. Through infrared telescopes, it lights up like a beacon. NML Cygni is losing mass at a furious rate, throwing off an Earth-sized chunk of matter every few months. Each pulse of the star causes another round of mass ejection, feeding the dust shell that surrounds it. In the constellation Sagittarius, near the heart of our galaxy, sits VX Sagittarii, a red hypergiant about 1,520 light-years away. It measures around 1,420 solar radii at its peak. It is bleeding into space at a rate of roughly 1 Earth mass every couple of months. The star is in a real sense evaporating, with material gushing out in every direction, creating a thick glowing envelope that telescopes can resolve as a fuzzy halo. VX Sagittarii pulses irregularly, its brightness changing over cycles of a couple of years. During bright phases, it becomes visible to the naked eye from the southern hemisphere. During dim phases, it requires a telescope. The material being shed by VX Sagittarii contains heavy elements forged in its core: carbon, oxygen, silicon, iron, which will become part of the next generation of stars. Without giants like this, there would be no carbon for life, no oxygen for water, no silicon for rocky planets. For many years, one star dominated the leaderboard of cosmic giants, Canis Majoris. It sits in the constellation Canis Major, about 3,900 light-years from Earth. In its glory days, Canis Majoris was estimated at around 2,000 solar radii. More recent measurements have brought that figure down to about 1,300 to 1,700 solar radii, still enormous, no longer the champion. Its outer atmosphere is so loosely bound that material peels away constantly, forming an extensive nebula of ejected gas and dust. Photographs from the Hubble Space Telescope reveal chaotic swirling clouds that look more like an explosion frozen in time than a steady stellar wind. The cause may be massive convection cells, each one the size of our entire solar system, bursting at the surface and launching colossal amounts of material into space. Canis Majoris is also dimming slowly over time as the growing dust cloud blocks more light. We are watching the star disappear behind its own breath. But the current heavyweight champion, the star that now holds the title of biggest known, is Stephenson 218, often shortened to ST218. It sits about 20,000 light-years from Earth in the constellation Scutum, inside a star cluster called Stephenson 2. Estimates place Stephenson 218 at around 2,150 solar radii. That is the most reliable current figure. At that size, the star would dwarf our entire solar system. If placed where our Sun sits, its outer atmosphere would stretch far past the orbit of Saturn, possibly out toward Uranus. Light takes about 9 hours to cross its diameter. That is longer than a workday. Light from our own Sun makes the same journey in about 2 seconds. The star is a red supergiant, possibly a red hypergiant. Its surface temperature is around 6,300 degrees Fahrenheit, cool enough to explain its deep red color. Despite that cool surface, it pumps out energy equivalent to about 440,000 times that of our Sun, almost all of it in infrared. The cluster around it is itself a cosmic oddity, a group of about 24 red supergiants all packed together, a remnant of a massive star-forming event about 20 million years ago. Most of those stars are already dead. Stephenson 218 is the largest survivor, but even Stephenson 218 sits right at the theoretical wall that prevents stars from growing any larger. That wall is the Eddington limit. To understand it, we need to look inside the star. A star is a constant tug-of-war between gravity, which wants to crush everything inward, and radiation pressure from fusion, which pushes outward. For most stars, gravity wins easily. For hypergiants, the radiation pressure is so powerful that it almost equals gravity. The Eddington limit is the point where those two forces are in perfect balance. Above that limit, the star's outer layers get blown away. Stephenson 218 is essentially hugging that wall. What happens if a star tries to grow past it? It begins to disintegrate, shedding mass faster and faster until its core is exposed and it transforms into a different kind of star. This is why finding a star bigger than Stephenson 218 is so difficult. The biggest measurements always seem to bump into the same physical ceiling. But there is a loophole. The Eddington limit assumes a star with normal present-day chemistry. In the early universe, when the first stars formed out of pure hydrogen and helium, the rules were different. Those first stars, called population 3 stars, could grow to sizes that would be impossible today. Without heavier elements to help cool the gas, the collapsing clouds had to grow much larger before they could ignite fusion. The first stars ranged from 100 to 1,000 times the mass of our Sun, possibly even larger. They burned at temperatures of 50,000 degrees Fahrenheit or more, flooding the universe with ultraviolet radiation that stripped electrons from hydrogen atoms and reionized the cosmos. They lived only a few million years before exploding as supernovae. The largest of them, those over about 130 solar masses, may have ended as pair instability supernovae, completely destroying themselves and leaving no remnant. Those explosions seeded the universe with the first heavy elements: carbon, oxygen, iron, everything that makes up our bodies. Beyond population 3 stars, there are even more exotic theoretical objects. One is the hypothetical quasi-star. A quasi-star would have had a black hole at its center, not a fusion core. As gas fell toward the black hole, it heated up and released enormous energy, supporting a gigantic outer envelope. Quasi-stars could have reached diameters of tens of thousands of solar radii. If you placed a quasi-star where our Sun is, its outer atmosphere would extend far beyond Pluto, swallowing the entire solar system many times over. They existed only in the early universe, and they may have been the seeds of the supermassive black holes that sit at the centers of galaxies today. Then there are dark stars, powered not by fusion or black hole accretion, but by the annihilation of dark matter particles. If dark matter particles can annihilate each other, they release energy that could power a star. Dark stars would be enormous, possibly millions of solar radii, and they could live for hundreds of millions or even billions of years. They would have been the largest individual objects the universe has ever produced, but we have no direct evidence they ever existed. Their existence depends entirely on the nature of dark matter, which is still one of the biggest mysteries in physics. So how big could a star theoretically get? For normal stars in the modern universe, the practical maximum is around 2,000 solar radii, where Stephenson 218 sits. For quasi-stars, the theoretical maximum is up to 100,000 solar radii. For dark stars, it could be millions. Beyond that, gravity would prevent any object from holding together as a coherent star. The material would fragment into many stars or collapse into a black hole. The size of a star is also tied to how fast light can travel across it. If a star were too large, internal communication through pressure waves and radiation would become so slow that the star would lose coherence and behave like a loose cluster of glowing material. Now, here is the haunting part about all these giants. The light from Stephenson 218 takes 20,000 years to reach Earth. The light arriving at our telescopes tonight left that star around the time humans were just beginning to develop agriculture. Whatever is happening at Stephenson 2E18 right now is unknown to us. It may have already exploded. The light from that explosion is racing toward us at 186,000 miles per second, but it will take another 20,000 years to arrive. The night sky is a time machine. Every star you see is a snapshot from the past. For hypergiants, that snapshot might show a star that no longer exists. We are watching ghosts. When a hypergiant finally explodes, the aftermath is dramatic. The supernova lights up the sky for weeks or months. The expanding cloud of debris plows into the surrounding gas and dust, creating glowing structures that can stretch for hundreds of light years and persist for tens of thousands of years. Many of the most beautiful objects in our sky are supernova remnants, like the Crab Nebula. Hypergiants also leave behind compact remnants. For most, the leftover core becomes a neutron star, a city-sized sphere of ultra-dense matter that spins rapidly and emits beams of radiation. For the most massive stars, the core continues collapsing into a black hole. And beyond the visible remnants, hypergiants leave behind a chemical legacy. Every atom of carbon in your body, every bit of oxygen you breathe, every drop of water you drink, every gram of iron in your blood traces its origin back to stars exactly like the ones we have been touring. You are made of star stuff, and much of that star stuff came from giants whose names you have just heard. But the biggest star ever to exist may not yet have been discovered. The Milky Way contains hundreds of billions of stars, and only a tiny fraction have been studied in detail. Many of the largest stars are hidden behind dust clouds, obscured by the structure of the galactic disk, or simply located in regions that have not been thoroughly surveyed. There are likely dozens, possibly hundreds of red hypergiants hiding in our own galaxy that have not yet been identified. Some may be larger than Stephenson 218. Beyond our galaxy, the Andromeda Galaxy, and billions of others each have their own population of giants, most too far away for detailed observations. Future telescopes like the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Extremely Large Telescope will survey vast numbers of stars in unprecedented detail, possibly revealing hypergiants that dwarf anything currently known. We may never identify the absolute largest star in the universe. The cosmos is too vast. But every new discovery pushes the boundaries of what we know is possible. The search for the biggest star continues, and perhaps the biggest star ever to exist died billions of years ago, leaving only its scattered remnants and the ripples it left in space-time as evidence of its passing. The universe is bigger than your imagination. The stars that fill it are bigger than your imagination. And the hunt for the largest of them all is a journey that never ends, one observation at a time, as humans look up at the night sky and try to understand the scale of what they are seeing. And that is the heart of it. The hunt for the biggest star is not just a competition, not just a list of numbers that keep changing. It is a mirror held up to our own place in the cosmos. Every time we measure a new giant, we are measuring ourselves against the impossible scale of the universe. We are tiny creatures on a speck of dust, using mathematics and light to reach across tens of thousands of light years and touch the surfaces of stars that would swallow our entire world without a trace. That act of reaching is what makes us human. The stars we have met on this journey, Sirius and Betelgeuse, Antares and Mu Cephei, VV Cephei, and Stevenson 2-18 are not just objects. They are milestones on a path of understanding. Each one teaches us something about how matter behaves under extremes we can never replicate in a lab. Each one challenges our models and forces us to refine our physics. And each one reminds us that the universe is not static. The biggest star you see tonight may be the biggest you will ever see from that point in the sky, because these monsters are always changing, always dying, always seeding new stars from their own ashes. There is a word astronomers use for this: cosmic recycling. The iron in your blood was forged in a hypergiant that exploded billions of years ago. The carbon that makes up the molecules of your DNA was cooked in a red giant that puffed away its outer layers into space. The oxygen you breathe was synthesized in the core of a star that no longer exists. You are not just looking at these stars from a distance. You are looking at your own origins. The boundaries between you and them are thinner than you think. So when you step outside tonight and look up at the sky, let the faint red glow of a distant supergiant catch your eye. Know that the light you are seeing may have been traveling for centuries or millennia. Know that the star that sent it might already be gone. And know that you are connected to that star by the deepest threads of physics and chemistry. The biggest star in the universe is not just a record to be broken. It is a living thread in a fabric that stretches across all of space and time. And we are part of that fabric, woven from the same stardust, bound by the same gravity, and driven by the same curiosity that has pushed humans to wonder, to explore, and to measure the immeasurable. That curiosity is why we built telescopes that can reach across galaxies. It is why we keep looking. And it is why the quest for the biggest star will never truly end. Because as long as there is a sky above us, there will always be something larger out there, waiting to be found.
Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer, even to the naked eye. Let's take a look at the life cycle of Betelgeuse. an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, Astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of the gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While Boat GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days. And the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shock waves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same Boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies? but some of them are quite mobile. So much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking: a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light-years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomenon, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015 opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea, or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity, distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equations. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter, but only leave. This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe. exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. While the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole of unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space, and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes, exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon, we'll be able to discover indirect evidence for the existence of these intriguing objects. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? in the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1, which leads to repeated gravitational interactions at the same point of the particles' orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1:2, 2:3, or 3:4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper belt, lies another fascinating story of celestial harmony. Neptune, the eighth planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the ninth, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence.